Today is the fourth lecture in the digital control part of 458-580. And what we're going to get to today is we're going to get back to state-space control, representation, control design, or whatever, which you did with Dave Ball earlier. But you did it for continuous time, right? So what we're going to do is we're going to get back there, but for discrete time systems. So the two topics really that I want to cover today, one is about how do we choose the sample time for a system. All along I've been using a symbol capital T which represents the sample time of the system, and in the tute exercise I make it up. It's 1 second, it's a tenth of a second or something like that. So I want to do a bit today of how do we choose sample time and what are the implications of sample time. So we'll touch on this topic again in a later lecture. We're going to have a fairly good crack at sample time discussion today, and then we're going to talk about state space form, as I mentioned. So let's recap some of the things that we've covered. It's been a while since we've had a lecture in this series. We've talked all along about what we want to do is to compute a compensator. We want to get rid of bloody resistors and capacitors and op-amps. We want to compute the thing. And so we started with a really simple example where we took a continuous time compensator G of S, and we turned it into a difference equation. A difference equation then is very, very simple and straightforward to compute on even the tiniest computer or microcontroller. We introduced a notation. So in the difference equations, we use the subscript k to represent the element in a time series. So k is the current one, k minus 1 is the one before that. So we introduced this operator z to the minus 1, which delays or shifts a signal by one time step. And that makes the difference equation a lot more tidy. It's a little bit like a Laplace transform. The z is a little bit like s. So we just introduced it as a convenience operator to represent a time shift, but more formally it was a z transform. And a z transform is a way of representing a sequence of numbers by a summation using z to the power of k, z to the minus k, which represents shift. So any signal that we sample at regular intervals, we can represent it by its z transform. And that's the fundamental definition of a z transform. You can look z transforms up in tables, you look them up on Wikipedia, and in the last lecture we actually derived a couple of these. You can derive all of them, it's not rocket science to derive them. Some of them are more tedious than others, but they are all ultimately derivable. Now, we looked at a number of different ways to discretize a continuous time system, and the simplest one is we said, okay, S represents derivative. So let's make the simplest derivative operator we can think of, which is up there, the backward difference operator, and we substitute that in for S, and we can turn a continuous time system into a discrete time system. And then we can do this with increasing levels of finesse. So the Tuston transform is a more polished or sophisticated version of that. We can use the Z transform, or we can use something called pole zero mapping, where we use an exponential to represent the link between Z, the Z plane, which is the discrete time representation of the dynamics, and the S plane, which is the continuous time representation of the dynamics. The link between them is through e to the power of st. And we're going to see these exponentials appearing quite a number of times in this lecture. So the other thing that we talked about in the last lecture, it's pretty important, is this mapping between the S plane and the Z plane. And it's a very strange mapping. Right? We take a band which is shown there in blue in the S plane, and we scrunch it up inside of a circle, which is shown there inside the Z plane. So the imaginary axis in the S plane gets mapped to the outside of the circle. The middle of that infinite band on the S plane gets mapped to a finite circle in the Z plane, and there are a few other sort of elements that are mapped there. They're all color-coded, and that was covered in the last lecture. If we consider the poles and zeros, we can map them from the S plane to the Z plane. And if they're stable, they live inside the unit circle. Now, if we go back here again, we see that the units inside the unit circle corresponds to the inside of that blue band. On the S plane, it's on the left-hand side of the imaginary axis, therefore it's stable. So stable poles must be inside the unit circle. A pole at Z equals 1 corresponds to an integrator. That's the same as s equals 0, maps to z equals 1. A pole at the origin, a pole at z equals 0, has got no equivalent in the s-plane, right? It's a discrete time artifact, and it corresponds to a delay of 1 time step. So pure delay turns into a pole at the origin. Another thing we talked about in the last lecture was the final value theorem, and we use this to work out the steady state response of a discrete time system. So we have the dynamics of a discrete time system. We multiply that by the z transform of the input. It might be a step input. So step input, the z transform of that multiplied by the z transform of the dynamics of the system, and then we apply the final value theorem, and that tells us what's the steady state response of the system to that step input. All right, so it involves taking a limit as z approaches 1. Another thing that we talked about in the last lecture was if we have a continuous time plant g of s and we have a discrete time compensator d of z, we have sort of a mismatch here. We have discrete time signals and we have continuous time signals. We need to join them together. And the way we do that is with something called a zero-order hold. So the input to the zero-order hold is a sequence, right? We can consider it as, on the time domain, as spikes, right? We have a value and then nothing, and the next time step we have another value, then nothing, and then next value, next time step another value. So we need to turn those spikes into something a little bit more continuous. So a zero-order hold does that. So an electrical analog of that is a digital to analog converter, right? You put in a digital value and out comes a voltage, and that voltage keeps coming out exactly unchanged until you write another value to the D to A converter. So a D to A converter implements this zero-order hold function. Its output is constant over a whole sample time. And that's really, really important. Now, this zero-order hold has actually got some dynamics. Its dynamics can be as important as the dynamics of G of S. So when we design a compensator, we need to design a compensator not just for the plant G of S, but for the plant plus the zero-order hold. So I'm going to just talk a little bit about that. In the last lecture, I introduced the dynamics of the zero-order hold, and here they are. So if you've got a plant, G of S, and a zero-order hold, this is how you incorporate that into the discrete time model. We covered that last time. What I'm going to do now is just derive this, because it's actually not too scary. So we've talked before about what a Z transform is. So here's a zero-order hold. And so what goes into the zero-order hold is an impulse, right? So if we put an impulse in at time equals 0, what comes out of the zero-order hold is a pulse, right? 1 time step wide. That's what a zero-order hold does. Converts a spike, a pulse, into a finite width pulse. Now, that output we can represent as the difference of 2 Heaviside functions. So everyone know what the Heaviside function is? What I wrote there is h. Yeah? Who can tell me what the Heaviside function is?
It's discontinuous. It's like 2 functions, but they have domain requirements. Like they're only a value for a certain period, and then another period might change instantaneously to another one.
Sort of. So the Heaviside function is also called the unit step. So it's 0 from negative infinity all the way up to 0, and then it jumps to 1, and then it's 1 up to infinity. So it's a unit step. So we can get a finite width pulse by subtracting 2 Heaviside functions. So h of 0 is a step that goes up at 0. H of t is a step that goes up at time t. The difference between those then is that waveform that I've drawn there on the right. Okay, so here's a zero-order hold. What goes in is a spike. What comes out is a finite width pulse. So we want to compute the transfer function of this thing. So let's take the Laplace transform of the input and the output. So the Laplace transform of a spike is 1. It's the simplest Laplace transform there is. It's not really intuitive, but anyway, there it is. That's what it is. And so the u in the Laplace domain is equal to 1. On the output side, the Laplace transform of a Heaviside function is 1 over s. And the Laplace transform is linear, so And there's also this shift operator. So if we have a shifted Heaviside function, then the Laplace transform of a shift is e to the minus st. And we talked about that in a previous lecture. E to the minus st is a shift of time in the Laplace domain. So I can subtract those two Laplace transforms, and this is the Laplace transform of the output, 1 minus e to the minus st all over s. And so the transfer function of the zero-order hold is simply the ratio. It's y over u, and it looks like this. So it's just what I gave you in the last lecture. This is how you can derive it. So it's another one of these things that looks a little bit intimidating, but you can actually derive it pretty easily. Now, there's an interesting thing about the zero-order hold. And this is an example of a continuous signal, a continuous sine wave in blue, and a zero-order hold version of that signal. And that it introduces some delay. You can see at some point the zero-order hold is exactly equal to the input signal, but then it maintains a constant value for a while the input signal keeps changing, and then it catches up, right? So sometimes it's the input signal with absolutely no delay, and other times it's the input signal with some delay. So on average, the amount of delay is about t on 2. The delay can be either zero, it varies between 0 and t. On average is t on 2. So we call that latency. So I've got a little cartoony example here about what latency is. So you're waiting the bus comes every hour. So if you get there just before the hour, you're going to get on the bus. Yeah? So you don't have to wait at all. If you get there just after the hour, bus is gone, you're going to have to wait for another hour. All right? You get there half past the hour, you're going to have to wait for half an hour. So the latency in these three cases is about 0, is almost an hour, and is about half an hour. So if you assume that you arrived at the bus stop with a completely uniform distribution, your average waiting time would be half the bus period, right? Your average latency would be bus period on 2, right? So that's what I mean by latency. So on average, the zero-order hold introduces a latency of t on 2. Now that's got some interesting consequences. Probably when you've done control units before, have you done Bode plots with magnitude and phase margin and gain margin? Yeah, those things fry my head. But anyway, you've done them, you know the concept, and that's good. So let's think about what does a delay, a constant delay, do to the phase of a signal. So here's a signal. In red is the original signal, and there's a delayed version of it in blue. And it's been delayed by a time, delta. Yeah? And the period of that signal is capital T. So the phase delay, the phase shift, right, is in units of radians, and it's given by this. So this makes some sense. If the delay is equal to 0, then the phase shift, the two signals will be in phase, the phase shift is 0, right? If the delay is equal to t, i.e. it's shifted by a whole period, then we could say the phase shift was equal to 2 pi. Also equal to 0, right? Because you wouldn't be able to tell any difference. So the phase shift as an angle is delta over capital T, where delta is the delay that we've introduced into the signal. All right? We know that that's true. So if we substitute these in, we end up with a relationship that says that the phase is equal to omega, is equal to the frequency times the time shift. So this means that the phase increases linearly with frequency, right? That's a very unusual characteristic. If you look at a first-order system, right, this is a single-pole system, we see that at the pole frequency, right, the magnitude breaks down, and we see that the phase shifts through 90 degrees. 2 poles, and the phase is going to shift by 180 degrees. So you're probably quite familiar with this representation. A delay is quite different. The phase just keeps increasing and increasing forever. And this is why it's very destabilizing. So if you think of it in terms of gain or phase margin, it's very destabilizing because the phase error just keeps increasing. So a delay has got a very interesting characteristic as far as phase is concerned. So you need to take this into account when you put a zero-order hold in your system. So we showed before how we can take the Z transform of our system, with a zero-order hold. There's kind of a hackier way to do that. And what we do is we just say that a zero-order hold introduces approximately a delay of half a sample period, and we can approximate it by this transfer function. It's called a Parde approximation. So we see that it introduces a new pole, a pole at -2/t. Now, intuitively, this makes a little bit of sense. If the sample period gets to be very, very small, as t goes to 0, then this extra pole that we've introduced moves out to -infinity. And we forget about stuff that's out at -infinity, right? We don't care about it. It doesn't affect our dynamics. So if the sample time is really, really small, the effect of the zero-order hold is negligible. But as t becomes bigger, and this pole starts to move into the region where the other poles of your plant live, then you've got a real problem. Well, not a real problem, but you need to take it into account. So if sample time is quite large with respect to the poles that already exist in your plant, consider it with either the Parde approximation or the proper zero-order hold and Z transform that we talked about a few slides ago. That makes sense? Good, good. So another way of looking at this, here back to Z transform again, and here's a Z transform for a cosine wave, and it looks just like this. It's kind of complicated, and you can derive it. I think it was a Tute example that probably nobody got to, but it can be done. And it's interesting because inside this Z transform is these two cosine terms, cosine of omega capital T. So the poles and zeros of this transfer function depend on the frequency of the cosine wave that you're generating. It also depends on the rate at which you're sampling it, on capital T. Now, there's a bit of a problem with a cosine wave, right? Because it's a continuous wave. It's periodic. It repeats. So let's say that I pick a particular value of omega and t that gives me that dot on that cosine wave. And we're talking, the axis now is omega t, the argument of those two cosine functions, terms that are highlighted in red, right? There's cos omega t. It's exactly the same as that omega t, right? So if I picked either of those two omega t's, where I marked with a dot, I'm going to have exactly the same Z transform. So Z transform is not unique. Now, also if I pick this one, the cosine is exactly equal to that one. So it's also not only every 2 pi does it repeat, there's also these reflections around pi. Yeah? So we can see that there are multiple values of omega t that plugged into the Z transform up the top would give you exactly the same Z transform. Couldn't tell the difference. So it's not unique. And this is a really big problem with sampling. I'm going to try and do a bit of an intuitive argument here. So let's say that cos omega t, we know it equals cos of omega t plus 2 pi I. Here I is not the complex number I is the integers 1, 2, 3, 4, 5, 6, yeah? So I don't want to use k because I use k somewhere else and it's all going to get horribly confusing. So I is another integer, right? So do we all agree that that's true? Yeah? Good. So therefore we can say that omega t looks like omega t plus 2 pi times I. So as far as this Z transform is concerned, this frequency looks like a whole lot of other frequencies that recur. Or we can, taking out the capital T's, we can say that this frequency omega looks like all of these other omegas. They're all going to give you the same Z transform. We've also got this reflection around pi thing that happens. So that gives us another set of similarities or ambiguities, and we get this set, right? So there are lots of frequencies that will give you the same Z transform. Z transform is all about sequences of numbers. So we're saying it will give us the same sequence of numbers, which is a little weird. So here's the first exercise for the evening, and I've given you the Z transform of a cosine wave, and I want you to write me the expression for its poles and zeros. Zeros are pretty easy. The poles might take you a moment or two. So can you work this out in your book? And anyone who's got an answer, come and write it up on the whiteboard. And I'll put my answers up and we can have a discussion. The way I tackled this is we set the numerator equal to 0 That's how we find the zeros. And so that can only be 0 if two things are true, either z equals 0 or z equals cos omega t. So that's what the zeros are for this transfer function, yeah? For this z transform. The poles are more complicated. So what we want to do is set the denominator equal to 0. And that then is, so z then is the solution of a quadratic equation given there in full. And by my reckoning, it comes out as cos omega t plus or minus j sine omega t. So close. Yeah. So that's pretty straight. That's the quadratic equation you learned in high school. You know, minus b plus minus square root of b squared minus 4ac all over 2a. Bit of simplification, the 2's go out. You end up with cos squared minus 1, which is equal to minus sine squared. The square root of that's j sine. There we go. Anybody say anything about that, about the poles, right? So what kind of shape is that? As omega t varies, what curve do the poles move along? Yeah, absolutely. It's a circle. So if I was to plot those, there's the 0 sitting there on the real axis at cos omega t, and on the outside of the unit circle is a point, cos omega t, j sine omega t. It moves around a circle. So the poles move around the circle and the 0 moves along the real axis. So that's pretty cool. So I made an animation, which is pretty interesting. So what I'm going to do is plot how the poles and zeros move as omega t increases. So have a look at this. All right? Here they go. They go all around the outside of the circle. Omega t is increasing. It's still increasing. They bounce off and come back. And if I kept increasing omega t, well, then they'd bounce off again, and then they go back again. So you can see that for particular values of omega t, let me just run that one again. There are multiple values of omega t that give you the same configuration of poles and zeros. It's not unique. I don't quite know what happens there at the end. Okay. So we have this ambiguity when omega t is greater than pi. Now this is really important. We call this effect aliasing. Right? So there are frequencies, omega t, scaled frequencies, that are not unique. So they're unique up to pi. Beyond pi, they get wrapped back and appear the same as frequencies that are in the range 0 to pi. So this is problematic because different frequencies on your continuous signal can look exactly the same in your sampled signal. So we require that the frequencies are less than pi over my sampling frequency. If a frequency violate that condition, we're going to get confused. Now this is a really fundamental thing. It's called the sampling theorem. It's attributed to two pretty smart guys, Nyquist again and Claude Shannon. Shannon's the information theory guy. He's the guy who gives us entropy as a measure of information. Very smart cookie, and they came up with what's called the sampling theorem. Sometimes he gets left off and it's just Nyquist sampling theorem. Sometimes it's just the sampling theorem. And the sampling theorem is that the frequencies that you're sampling have to be less than 1 over 2t, or they have to be less than your sampling frequency divided by 2. So let's say I'm sampling a signal at 1 kilohertz. Right? So my sampling frequency, fs, is 1,000. That means that the frequencies that I can represent uniquely are all the frequencies up to fs on 2, up to 500 hertz. Any frequency above 500 hertz is going to cause me confusion because it's going to come back looking like a different frequency, and it's going to confuse the hell out of my control system. So yet another, I'm just giving you a whole lot of different ways to think about this problem because it's really deep and it's really important. So I came up with all the ways I could think of to represent this. Okay, remember we gave this diagram in a previous lecture. Yep, so here was that blue band from the S-plane gets mapped into the middle of the unit circle. And that imaginary axis is the outside of that unit circle, right? So that imaginary axis is infinitely long. And so it wraps around and around the unit circle over and over again, right? Not uniquely. So it's not an infinite thing wrapped around it. It's an infinite thing going around and around and around the unit circle lots of times. And notice that the limits on that band, it's from between plus and minus pi over t. That's the number that we came up with just before from the Nyquist sampling theorem. So there was that bit of the real axis, how it gets mapped, the red bit. That's how the blue bit gets mapped. That's how the outside of the strip gets mapped. And if I consider a pole that's here in the S-plane, and we can map it to there in the Z-plane, but so does all those places. Upwards forever, they all get mapped to that one dot in the Z-plane. Really important to remember this. So a few slides ago, I gave you this aliasing relationship. So what I want you to do is figure for me the frequency of two cosine waves that look exactly the same as a 20 hertz cosine wave when they're sampled at 100 hertz. Can you remember the relationships that I put up there before?
Like the omega plus 2 pi.
Yep. Yep. And the 2 pi I minus omega. Yep. Right. Stagger over to the board. It was omega plus I 2 pi, and it was 2 pi, I think it was on t, I minus omega. Yep. Anyone got one? What's that? Correct. Someone say 80? Yep. All right. I'm going to show you the way I did it. So that was our sampling period, 100 hertz, 10 milliseconds. We know that omega is equal to 2 pi times 20. So I call it omega dash. That's an aliased version of our input signal. It's all a bit ugly with all the 2 pi's, and I'm going to flick it between radians per second and hertz, and I end up with this relationship here. So the aliased frequencies is 20 plus 100 times anything. So 20 is going to look like 120, 220, 320, 420. All those frequencies are going to digitize to the same as 20 hertz. Let's do the reflection one, and it looks like this. So 20 is going to look like 80, is going to look like 180, 280, and so on. Yep. So the strange and sad truth is that 20 hertz looks identical to 120 hertz and 80 hertz. If you don't believe me, I plot this in MATLAB. So here's 20 hertz and 80 hertz, sampled at 100 hertz, and the dots show where I sampled it. So if all I do is sample the signal at 100 hertz, it's like having my eyes shut most of the time and occasionally opening them, and I can't tell the difference between these two signals. They look exactly the same at the sampling interval, and this is called aliasing. Let's look at the other one. This was 20 hertz and 120 hertz, exactly the same deal. All right, so that sort of shows it pretty starkly. These two signals look exactly the same if you sample them. So there are some important consequences of this. One important consequence is if you've got a sensor that's feeding into a digital control system, and say your digital control system's running at 100 hertz, into your A to D converter, you do not want to have anything above 50 hertz, right? Because if you've got 51 hertz going into your A to D converter, it's going to digitize to the same as 1 hertz, and it's going to confuse your control system no end, right? 52 hertz is going to look like 2 hertz. It's going to look like a really low frequency. So there's a whole, what you need to do is to filter the input signal before it goes into an A to D converter through what's called an anti-aliasing filter. Typically that's an analog filter that's designed so that it's got a lot of dB down at what's called the Nyquist frequency, at this sampling frequency over 2, called the Nyquist frequency, right? We need to have no input signals above that frequency. So we need to introduce an analog filter typically to eliminate that. If you say your sensor is something like a gyroscope or an accelerometer, typically what you do that's mounted on a machine like say an aircraft that's got a lot of engine noise that might be higher frequency than the rate at which you're sampling, then what you do is you mount that sensor on some sort of elastic material. So you create a mechanical filter so that those high frequency components don't get into the sensor in the first place. So there's a lot of ways you can get rid of this high frequency information. And we'll touch on these again in a later lecture. But that's called an anti-aliasing filter, and it's a really critically important part of any system where you digitize a continuous system, digitize a continuous signal into an A to D converter. So there are some rules of thumb when it comes to digitizing systems. Typically, you want to aim for a sample rate up to maybe 30 to 50 times the frequency that you're interested in, right? So that's a rule of thumb. If you do that, then you can use the simplest possible method to discretize your system, that backward difference equation that we talked about. When the first time we discretized the system, I made that substitution. That will work well if your sampling frequency is high, 30 times the bandwidth. If your sample rate's between 10 and 30 times the bandwidth, then you should add an approximation to the continuous time system. Use that part A approximation, for instance. If your sample rate's quite low with respect to your bandwidth, then you really should use the Z transform and the zero order hold. So these are some useful rules of thumb that relate your design methodology to the sample rate. And we've talked about why sample rate is really important. Any questions on that? Because I'm going to leave sample rate now and I'm going to get stuck straight into state space design and representation. Alrighty. So this is a slide that I stole from Dave Ball. So I'm guessing you've seen it in earlier lectures in this unit. And we have this representation where we use matrices and vectors. So X is the state vector, and A is a matrix. If you've got n states, A is an n by n matrix that relates the state to the derivative of the state. B is a matrix that couples the input. U is the input to the system into the states. So B connects the inputs to the states. A tells us that how the derivatives of the states vary as a function of the states. Matrix C says how the outputs are related to the states. And D is very, very rarely exists in most systems that you'll ever come across. D is almost always 0. And it's much, much easier if it's 0. So the C matrix says how the states are connected to the outputs. And I think he talked a little bit about how you convert a transfer function to a state space system in sort of phase variable form. Companion matrix form looks something like this. But you could do exactly the same thing if your transfer function was in Z instead of in S, right? You could convert it to a state space, discrete time state space representation, just like that. Everything that you've learned that you can do in continuous time, you can do in discrete time. So that would be an easy way to get going. But we're going to approach it in a slightly different way. So here is our continuous time system up the top, and I'm going to do a Laplace transform of it. So where we have the dot, x dot, we replace that with s times x, because s is the Laplace transform of the derivative. And we change all the little x's to capital X's. And now we have a Laplace transform of our state space system. And this is a substitution we used long time ago for a transfer function representation. So, okay, I can see an S, and here we've got this substitution that worked for us once before. Let's just go for it. Let's do it. So here we go. I'm going to make this substitution. So where I had Sx, I'm going to have x minus x previous divided by the sample interval. Plug it all in. I'm going to do a little bit of rearrangement. And I'm going to run through a lot of equations tonight. You don't have to write them all down. They're all in the notes. And then I can rearrange that. I can take that I minus TA over to the other side, and I end up with something that's a bit big and ugly. But I can just introduce some new variables to represent those big ugly expressions. And here I have a discrete time state space representation of the system. So before in a state space representation you had x dot equaled ax plus bu. In discrete time we say the next state is equal to some matrix times the current state plus another matrix times the input. So that's the only difference. On the left-hand side now we have the next state, whereas before you had the derivative. So here is a very crude approach to turning a continuous time state space system into discrete time. And there you go. Now there's a more proper way to do it, and there's quite a lot of maths here, so just sort of lean back and try and get the general picture of what's going on rather than the detail. So if I'm trying to solve a differential equation, which is ultimately all of these things are differential equations, there's two solutions, there's two parts to the solution of a differential equation. We have what's called the homogeneous or general solution. That's the solution when the thing's unforced. It's got no input, right? So you just kind of give it an initial condition, you let it go, and it will do something. This is called the general solution of the differential equation. And so I'm going to say that this is the general solution of the differential equation is given by this. I've thrown away the BU term, because I don't care about the input here. And I'm going to say that at time 0, at t0, it's got an initial state, x0. So I'm going to push the system into some state, I'll let it go and watch what happens. So I can write a general form for what it does as a Taylor series expansion, right? Taylor series expansions are useful for lots of things. So here I write it in completely general form, an infinitely long Taylor series. Now, I know that at time t equals 0, at time t0, x is equal to x0. So all of those terms, with the a1, the a2, and so on, are all going to be equal to 0. So I can say that a0 equals x0. Can everyone see how I do that? Yeah? So when t equals t0, then the terms in those brackets all go to 0. Yep, so all I'm left with is x equals a0. And x at time t0 is x0. So I can write that. I've solved for one of the coefficients. Now, I'm going to say x dot, and I just take the derivative of the Taylor series, and that's pretty easy to do. A0 goes away, and all I've done is compute the derivative of the Taylor series on the line above it. Now we know that x dot is equal to a times x, because that's one of the equations we've got right at the top. So I can whack that in there. And now I can say, doing the same trick as before, when t equals t0, all the terms in the brackets disappear, and I can say that a1 is equal to a times x0. And I keep doing this trick. And now I take the second derivative of the Taylor series, and I know that that's equal to x dot dot. Going up to the top there, x dot dot is equal to a times x dot. We know that x dot is equal to a times x, so therefore we know that x dot dot is equal to a squared x. And I solve for another coefficient. I solve for a2. And I could do this all night and all of tomorrow as well, but I'm not going to. But you get the general idea. So here's our Taylor series, and here are the coefficients that we've worked out so far, plus one more that I added in. And we can do this trick, and we can do some tidying up. We end up with x is equal to an infinite series times x0. Now, you're probably not going to twig to this, but what's inside the curly brackets is exactly the same series as an exponential. So e to the x is equal to this series that I've got over the bottom here. So that means, kind of strangely, that x at time t is equal to e to the power of a matrix times t multiplied by the initial state. And this is really, really powerful. So this is saying that if I know the state at time t0, then if I can compute that matrix exponential, I can work out its state at any time into the future. Anytime t, I know t0, I take the difference, multiply it by a, raise e to the power of a, and I can do that. Now, MATLAB eats that up really easily. You can give MATLAB, you say exp of a matrix, and it computes exactly the right thing. Otherwise, most calculators and phones will barf if you try and exponentiate a matrix. But the way the MATLAB does it is to actually compute the power series, right? And it converges quite quickly. So the same way it computes e to the x, it can compute e to a matrix. Okay, so that's fun. So these exponentials come back again. The exponentials keep coming back. So there are some properties of this matrix exponential. So I can work out the state at time 1. I can work out the state at time 2. And just using this general property of exponentials, that if I multiply two exponentials together, the result is an exponential with the sum of the exponents. So if I use the exponential to get me from time 0 to time 1, multiply that by an exponential that gets me from time 1 to time 2, that's the exponential that would get me in one step, in one hop, from 0 to 2. Yep, that's just fundamental properties of exponentials. There's nothing magic here about them being matrices. But what that means is that I can get from the state at time 0 to the state at time 2 in 2 steps by taking it to time 1 and then from time 1 on to time 2. We can also derive these properties as well. So if I use the exponential to get me from time 0 to time 1, I can then use the inverse of that to get me from time 1 back to time 0. So I can use these exponentials not only to propagate the state of our system forward in time, I can also use it to go backwards in time. It's very, very powerful. Now there's the other part of the solution of a differential equation. It's called the particular solution. And in this case, I'm going to propose that the particular solution looks like this. This is a standard trick in solving differential equations. It's an exponential multiplied by some vector. V is a vector here. And I'm going to take, this is the definition of the dynamics of our system, and I'm going to do some substitutions. And so what I've done is taken the derivative of the top line, and I apply the chain rule. So that ends up with the derivative of e to the a blah, which is a e to the blah multiplied by v plus e to the a multiplied by v dot. Plug all of those things in there. Some things cancel out, and I end up with this quite simple expression as the particular solution of my differential equation. Simplify it to get v dot. There's v dot, and I want v. I want to know what's this signal v. It's a vector, yeah? And so I do an integration. I substitute this back in. Integration is getting a bit more complicated. I move the exponential inside the exponential. Do some more simplification. This is all in the printed notes. And I end up with this equation. And then this one. But now it's getting a bit simpler because now I'm into discrete time. So I'm saying x at time kt plus t, at the next time step, now I'm starting to get it into the form of bringing in the capital T, bringing in the sampling interval. So it's now coming into the form of the current state and the previous state. I can do a little bit more here, and I can make use of the fact that the input, the u here, is coming out of a zero-order hold, so it's constant over the sample interval. And that makes that integral really, really easy, because integrating a constant over a time period is just the constant multiplied by the width. And so we end up with something that looks like this. So this is the discrete time version of our original state space system. So we have our matrix exponential there, and then we have this big ugly integral multiplied by our old B matrix. So we write this, same equation again, and the common symbols for these two is capital Phi, that's the circle with a line through it, to represent what we call the state transition matrix, and a capital gamma to represent the input distribution matrix, right? So we've gone through all that maths, we've gone through the derivation, and we end up with now a discrete time representation of our continuous system. So A has been transformed into Phi, B has been transformed into gamma. And the C matrix is unchanged. The states are the same as they were before. It's our representation of the way they change is now different. Instead of it being a differential equation, we now have a difference equation. We now have the next x in terms of these things rather than the derivative x in terms of these things. The x still means the same thing. They're still your process state variables. I'm going to get you to do a really simple example. So I'm going to give you this continuous time system. For a sample time of 1 second, I'm going to get you to compute for me what is the state transition matrix. I probably should be a bit more clear about that. So have a... Maybe so I haven't actually phrased it very clearly, so I might just go on and solve it rather than get you guys to do this. So this is what I did. Right, there's my transfer function at the top in the plus domain. I multiply it out. I turn it back into a differential equation, so I turn the s into a derivative operator. I choose my state. This is a very simple system. It's only got one state. So I choose my state x to be exactly the same as y. So x equals y, x dot equals y dot. And so I can represent the dynamics very simply there as x dot equals minus 1x plus u. So our A matrix in this very simple state space system is minus 1. It's a very small matrix. It's a 1 by 1 matrix. Yeah? And so the discrete time version of that phi is simply e to the minus 1. Okay. Is it making any sense? Good. We want to talk about the poles and zeros of this discrete time system that we've created. And the way we do that is we write the next state in terms of the previous state. This is the unforced solution again, the homogeneous solution. So the next state is a function of A times the previous state. Now we can use the shift operator, the Z transform in here. So something that's one time step ago is the same as a signal multiplied by Z to the minus 1. So we've Z transformed it at this point, really. You can do some rearrangement, put the Z over the other side, move both of them onto the one side, and we've got something equals 0. And then we can factor it. It looks like this. Now there are two solutions to this. Yeah? What's one solution? Correct? Well, sort of. And the other, clearly if x equals 0, that's going to be true. So that's the boring solution, is x equals 0. The state is equal to 0. That's not very interesting. A more interesting solution is this one, is when the determinant of a minus zi equals 0. then all this will be true. So this is the poles of this system are the values of z for which the determinant of a minus zi equals 0. And that's the eigenvalues of the matrix A. Yeah? Now, since this is discrete time, I probably should have used phi in there, not A. Yeah? So we take the eigenvalues of the phi matrix, and they will give us the poles in the z-plane. So, sorry about that. So that's exactly the same as for the continuous time case. And I'm not sure if you did this with, you created a state space system, and you took the eigenvalues of the A matrix, and they are the poles, yeah? Good. All right, so it's exactly the same things here. The eigenvalues of the equivalent matrix, which is now the phi matrix, are the poles on the z-plane. Now, when you look at the eigenvalues of your A matrix, you wanted them all to be in the left-hand plane. On the z-plane, I want them all to be inside the unit circle, because that's where stability happens. I'm just going to do a really quick little thing on eigenvalues and eigenvectors, because they're things that confuse a lot of people, and to my mind they're pretty simple, and they crop up a lot. An eigenvector, if A is a matrix and V is a vector, it will transform the vector. Yeah, I did this in 339 the other night. So we can think of A as a matrix that transforms a vector into another vector, right? So we have a matrix, we have a vector, and the transform vector. So if I consider that V is the input vector, it gets transformed by the matrix into another vector, V prime, which is shown there in red. Yeah? Give a different vector, it will transform in a different way. This is a characteristic of the matrix A, the way it transforms vectors. But there will be a vector V which will be transformed into a vector parallel to itself. Yeah? There will be only one, there will be a very small number of vectors for which this happens. Yep? Here's another one. V is transformed into a vector that's parallel to itself. Now, it may not be the same length. It may be the same length. It may be bigger, it may be smaller, but it's parallel. So there are a couple of vectors, a few vectors which are really special, and that matrix transforms them into a vector with exactly the same direction. Yeah? Those vectors are called the eigenvectors. Yeah? And the length by which they're scaled is the eigenvalue. So eigen is German, and it means something like own vector. It's a special vector that belongs to the matrix. Yeah? And so these two things are true. The matrix A transforms a vector V into another vector V prime. But in this special case, the vector is parallel. So it's multiplied by a scalar, lambda. So two vectors, and lambda is a scalar. Yeah? So if those two things are true, we can crank through some maths, and we end up with this relationship, pretty much like the relationship we had before. To solve this, if we solve that equation, the solutions for lambda are the eigenvalues. They are the values for which this determinant becomes equal to 0. A is the matrix we started with, I is the identity matrix. You end up with a polynomial, solve it for lambda, they're your eigenvalues. Substitute them back in, and you get, that shouldn't be an O, 0 on the side. No, ignore the 0 that's next to it. And then you get the eigenvectors. So for every eigenvalue, you do the substitution and you get the eigenvector that corresponds to the eigenvalue. So they're really important. So in the case of a dynamic system, the eigenvalues are the poles. The eigenvalues of the system matrix, A or phi, are the poles. V is a vector in this case, and it's related to what are called the modes of a system. I found this little YouTube thingy which looks at modes of a vibrating beam. And so this is a beam, and it's pinned at each end, and this is one way it can move. This would be one eigenvector of a system, would correspond to this kind of motion. This is another kind of motion. So this system would have another eigenvector that represents this kind of motion. And there'd be yet a third mode, corresponds to yet another eigenvector of this system. So the general solution is a linear combination of the three eigenvectors, or the three modes. So you end up with this kind of quite general motion of the dynamic system. But all of these motions that you see are a linear combination of those three fundamental modes. The mode like this, the mode like that, and the mode that looks like that, I think. Yeah? So that's what the physical interpretation is of an eigenvector. Anyway, enough about that. Our system's also got zeros. So we've got poles and we've got zeros. So the zeros are when the output of the system equals 0. So it's kind of quite clearly and obviously named. Zeros are when the system's output is equal to 0. So y equals 0. And since the output is equal to c times the state, that must be true. And we can make these substitutions. And we can keep doing this. And we end up with this big matrix, it being equal to 0. And that will be equal to 0 when the determinant of that matrix equals 0. So if we know for our discrete time system, the phi matrix and the gamma matrix and the output matrix C, pump them all into, build a matrix, take its determinant, and that will tell us the zeros of the system. Now, of course, you can do all this stuff in MATLAB, and you should. So in MATLAB, you can create a continuous time system using the function SS. So if you know the A, B, and C and D matrices for your system, put them into the SS function, and it produces a MATLAB system object. So a system object represents the dynamics of a system. If you know the transfer function, you know its numerator and denominator, you use the TF function. It also produces a dynamic system object. Once you have a dynamic system object in continuous time, you can convert it to a discrete time system using the C to D function, continuous to discrete. So continuous time dynamics, put them into the C to D function, tell it the sampling interval, and bang, it will produce you a discrete time system. You can tell it how to discretize it. You can tell it to use Z transform or Tustin or backward difference or a few other options that it knows about. It's got a whole bunch of options that you can give it. If you've already figured out the phi and gamma and C and D matrix, then you can build a system object using the SS function. The only difference to above is that I've given it a sample time. I've given it this fifth argument with the sample time. It tells MATLAB that it's a discrete time system rather than continuous. I can do the same thing for a transfer function. If I have two polynomials in Z, and we've looked at those in earlier lectures, numerator and denominator, all polynomials in Z, I can create a discrete time system. If I have a discrete time system, I can get out the phi and gamma matrices by using the SS data function. If it's discrete, if it's continuous, it will give us the A and B matrix. Here it gives us the phi and gamma matrix. And I can work out the poles by using the eigenvalue function, or I can use the function T zeros to find out the zeros of the function. Everyone good with all this? We covered quite a lot of material. I've got a little bit more to go, and we'll probably go over some of this again in the next lecture to kind of bed it down. So just kind of let it sort of wash over you and try and just pick up the big picture ideas here. Pole placement design. You did this for a continuous time system. You do it in exactly the same way for a discrete time system. So here I've written the discrete time dynamics, xk, phi times xk minus 1, gamma times the input. If the input to the system is a linear combination of the states, minus k times the state vector, then I can substitute that in and I end up with a system whose closed loop poles are given by phi minus gamma times k. Yeah? So to design my controller then, what I want to do is to design k such that that term that I've highlighted has got its poles at a nice location inside the unit circle. And there are some ways you can do this by hand for a simple system. In MATLAB, the easiest way to do it is use the place function, and I give it the dynamics of my system, phi and gamma, and p is a vector that contains the desired locations of the poles. So if it's a second order system, phi is a 2 by 2 matrix, gamma is a 2 by 1 matrix, p would be a vector that contains how many poles? Second order system, it's got 2 poles. I have to tell MATLAB where to place 2 poles. So p is a vector that contains 2 poles. Now, they could be 2 real numbers. It could be minus a half and minus a half. That's a silly number. For z-plane, it'd be better to say a half and a half. Yeah? If they were complex, then they have to be given as a conjugate pair. So if I gave a pole like, say, 0.5 plus j times 0.3, the other pole would have to be 0.5 minus j times 0.3, because poles travel in conjugate pairs. Yeah? If you didn't do that, MATLAB would complain at you. So that's how you do pole placement design. It's really pretty straightforward. And typical control design scenario, what you do is you choose some poles, you'd simulate it, you'd look at the step response, see if it looks reasonable, move the poles a little bit, generate a new pole placement controller, simulate it again, and you go, typically in control design, you go round and round this design loop until you get a response that looks somewhat reasonable. Now remember when we designed phi and gamma, to get those we had to choose a sample interval. Yeah? So we've already chosen the sample interval for our system before we've gone on to designing the state feedback controller. It might be that you find that you just can't get a decent control. You then go back and say, well, okay, maybe I should sample a bit more quickly. I'll double the sample rate. Redigitize the system, get a new phi and gamma, and then play the state feedback control game all over again. Now, I hate it when things fall to the floor. I've got another pen. I've got a black one. What's one of the limitations with a state feedback controller? What do you need in order to compute state feedback?
Sense the state.
Yeah, you need to sense the state. Now, for some systems, the state is very easy to measure. If you're a vehicle, then the state is probably its position and its velocity, and you can measure that from the odometer and the speedo. If it's a Segway robot, then maybe one of the states is the angle and another state is the angular rate, and you can measure those from a gyro. But often that's not always the case. Sometimes the state is not measurable. It's some physical process deep inside the system and you can't actually get your hands on it. So I believe Dave talked to you about observers or state estimators. So he gave this diagram, which I've purloined, where you have the plant and you have this thing called an observer, and it sees what goes into the plant, it sees what comes out of the plant, it's got a model of the plant, and so from that it can infer the state of the system. So the state of the plant is hidden, but if I've got a good model of it, I know what goes in, I know what comes out, I can estimate that state. And once I've got the estimated state, then I can do the state feedback trick. It's all pretty simple. So here's another way of looking at this. Here I've got U, which is the input, and it goes into the plant. And the plant's got a state, which I can't really see, which goes through the C matrix and comes out as Y. So that's the output of the plant. That's what I can actually see. I want to get my hands on that XK, but I can't. I pretend that I can't. So all I can get my hands on is Y. So I build a clone of the plant, a model of the plant, and I feed the same input into it, and it's estimating me the state. And I call that X hat. Hat means an estimate. And I put that through the output matrix C. I know what C is, right? And I get an estimate of the output of the plant. Now, if everything was really good, if my model was absolutely perfect, right, then that Y hat would be exactly the same as Y. But that's really unlikely to happen. And particularly if I ran the estimator for long periods of time, eventually those two things would diverge. Because it's unlikely, two things are unlikely. One is that I would have a model that was really, really perfect of my plant. And the other thing is that the plant's parameters might change over time. You know, it might warm up, friction levels might change, all sorts of things, air pressure might change, all sorts of things might change that would affect the parameters of the plant. So I can't rely on my model being accurate. So what I do is I take the difference between what the output of the real plant is and what's the output of my pretend plant, my model of the plant, and ideally that's 0, but if it's not 0, I get a difference signal, and I multiply that by a gain, and I push that back into my model to correct it. So if those two things are in discrepancy, I generate a signal and use that to push the state back towards a value that minimizes that error. So it's actually a feedback loop that I've applied here that minimizes the error on what the model is estimating. A couple of ways we can do that. So inside the model, I could just have this equation, which simply says my model, the output of my model is the previous state multiplied by phi and the inputs. This is what we call an open loop model. It's not responding to any of this, to this error signal. So a more sophisticated one, a closed loop one, looks like this. So the next state is based on the previous state. We've got this state transition matrix phi, which is a reasonable estimate of what the state will be at the next time step, given we know what it is now. And we allow for the fact that the input is going to change the state, and we know the gamma matrix. So those first two terms are our best estimate of what the next state will be. But now what we do is the feedback term on the end says if there's a discrepancy, we multiply that by some gain and use that to push the state the right way. So we have to design this feedback bit, this L matrix, in such a way that this is stable and not unstable, and that would be bad. So that's what we're going to talk about next. So this is the dynamics of the estimator, of our model. Simply copied it from up there and rearranged it a little bit. I've lumped all the xk terms together. And so this then are the closed loop poles of our estimator. And I think you probably did this for a continuous time estimator. Yep. So we have the closed loop poles. So this is one of the design parameters. We need to choose L such that the estimator poles are stable and fast. As a rule of thumb, you want the estimator poles to be somewhere between 5 and 10 times faster than the poles of the plant that you're trying to control. So that means that your estimate of state is tracking really closely the real state of the plant, and then your other controller is trying to move the poles of the plant to their desired values. So this is the second design. This is the second part of the design that you need to do. And this L is called the observer gain. And that's really a summary. You want them to be faster than the closed loop plant poles. You want them to be inside the unit circle. And to do it with MATLAB, to do pole placement again, you use the place function again, but what you pass to it is phi and the transpose of the C matrix. Yep. So it's the same function we used before to design the controller, that same function to design the estimator, but we use C transpose instead of gamma, and P is a list of the poles of the estimator. And typically the order of the estimator is the same as the order of the plant. Second order plant, second order estimator, another two poles that we need to pick here. So this is pretty much the last slide. If we bung all this together, we end up with two blocks. We end up with our plant block, which has got a U going in and a Y coming out. We have an estimator block, which has got an X hat coming out, and it's got a U and a Y value coming in. You've got the other guy's Y coming in. All right? So that's how it works. This is how you connect the estimator to the plant. This is where the state feedback gain is up there. So we have the estimated state. We have the desired state of our plant, which I called X star. Take the difference of those, multiply it by state feedback matrix, and push that into the system. And there you go. That's how you do state space design, controller design, and estimator design for discrete time systems. You can really recycle a lot of the stuff that you've learned earlier for continuous time. All that really required now is to try and put some of this into practice in pracs and tutes. Any questions?